Very good. Yeah, sorry for the late start here today. Today we are only in the third lecture in the series because we had twice no lecture this term already. There's no further missed lectures planned so far, at least from my side. In any case, the plan for the lectures is in the CMS, so you can follow this. For today, the main topic would be drone sensors and sensor manipulation. We didn't fully finish with last week's or 2 weeks ago slide set with the last slide set, so I will probably also briefly go over the rest of the slides there. And before I start, are there other questions or comments? So we had the first exercise given out already. There is a good number of hand-ins that I see, so many of you completed that exercise. The exercise instructions for the second exercise are already handed out, and they are, we haven't created the group feature thing on the CMS yet and the submission thing in the CMS, but we will do this today probably. Yeah, just to let you know, the exercise instruction for the second exercise are out already. Just this kind of submission thing we need to create today. Or rather, yeah, it is created by now already. I pinged someone before the lecture. Okay, very good. So, any other questions, any other things we should discuss before I start with the main content of the lecture? Nothing. Very good. Then, yes? Yes. Yes. So we will have to grade the submissions first, and then there will be some short feedback together with points via the CMS as well. Okay. And then if you have more questions, you can always contact us and ask. But we didn't grade them yet. So yeah, let me just switch over to the other slide set that we didn't finish last time because, well, maybe some of these things you've seen in the exercise now already as well, but let me just briefly go over this so that we looked at the slides. I believe in the last time we came under this slide essentially, and then we didn't start yet with the drone software part. And this is, you might have looked at these slides already on your own, but let me just go through them now as well from my end briefly. So this is essentially was supposed to set you up as well more for the ArduCopter software, which maybe some of this you've seen already, at least you have installed it in exercise 1. Yeah, so what is then just an overview of what ArduCopter is, how the software is organized. You have, let me open my pointer here again. So we have, in general, it's set up like this, that we have several different threads that are handling, for example, sensor readings. And then there's this main cycle, the scan cycle, which is doing the real-time control. And then there is also this Kalman filter, for example, run in the main loop. So what is happening here? We have this background thread that is always collecting the different kinds of sensor information, inertial sensor, barometer, GPS, and so on, for example. This is feeding it into the extended Kalman filter stage. We have the main loop running in ArduCopter all the time. That is then essentially also initiating the Kalman filter. And then after the Kalman filter has essentially computed new state estimation for the values for the state of the drone, then we go into the next stage of the control, which is update flight mode. The flight modes, I'll talk about them in a second as well, a little bit more. And then after, depending on the flight mode, then we do go into the more low-level control of the physics of the drone. The mode stabilize, position control, altitude, attitude control, and motor and servo control. So we're going down in the really detailed control of the drone. And then through a hardware abstraction layer, we are then essentially converting these signals appropriately into analog signals or whatever, and sending them out to the hardware, for example, via these pulse width modulation signals that we briefly saw in the last lecture. Okay, so this is mostly to just give you an overview of where things are living, also in terms of where the files might be located and so on, because you might want to look more at them in the current or upcoming exercises. So what are the flight modes? So essentially in ArduCopter, you have different ways how you can operate the drone. There is There is, for example, a stabilized mode where the operator might want to do manual flight, and then so the operator is controlling the thrust and the yaw directly. So just essentially, you could say just steering it, yeah. So rotating it and then controlling the speed. And the vehicle maintains roll and pitch angle, for example. There's altitude hold mode where the drone will always hold the current altitude. And then you can just rotate the drone around if you wanted to. Loiter mode where it hovers in place. And again, we control roll and pitch angles. Auto mode where you define actually a predefined flight plan. So this is now really this mission planning stage where at some point in the past, you defined waypoints that you want to fly along. Then these waypoints are handed over to the mission control module on the drone. And that is then determining the immediate flight actions to be taken by the lower real-time control of the drone. You have a return to launch mode, which just the drone returns to wherever it thinks it took off from. This could be, for example, as a safety feature, or if it lost control to the controller otherwise. There's a guided mode where you could have, you could follow a target and then the target might be moving or something like this. And acrobatic mode, if you want to have full control, acrobatic and sport mode, essentially, if you want to have full control over, lots of low-level control of how the drone moves. If you want to have control of roll, pitch, thrust, yaw, and all these things at the same time, you can use these modes, yeah? So maybe now you see with all these different modes why we need to know what the flight mode is before we then go into the actual low-level control tasks or commands that are going to be sent to the actuators. And you probably all did this already now. You've seen this, you know how it looks, yeah? So that you can then play around with these kind of different modes in the autopilot simulator, for example. Was there, so some of you contacted me before and they were concerned about their operating system and so on. Is there still any issue with the operating system, or you were all able to run this autopilot simulator somehow on your hardware or software? Some people had fancy M2, M3, M4 processors or something like this. This was okay in the end or not? Sorry? But this is an Apple M2, M3, whatever? Okay, because the problem with the M2, M3, and whatever is then that you can't natively run Ubuntu. But I guess either the person is...
But I'm using the virtual machine and I have Debian on that.
Okay, but then you have a full virtual machine and you just emulate x86. Yeah, okay. Okay. So at least autopilot is, and also there's no issue to run it on there. Good to know, because this sometimes creates issues with it. Yes. Potentially, yeah. I forget if this was supposed to be an exhaustive list of flight modes or just. Yeah. It's actually all too much text on this slide already. I might have just left it out because there was too much on the slide. Yeah. And then, so what you're doing if you're now running in the simulator, let me see if I missed anything here. So here in the simulator, of course, okay, you know all of this now. Last time it would have been new to you, yeah? So you can observe in 2D how the drone is moving around the missions and so on. And what you are essentially doing is you're doing this as a software in the loop, yeah, because you don't have a real drone that you're interacting with. You have technically, I guess, the autocopter controller binary that you compiled in the end for your host architecture that is natively executed as an ELF. That is then communicating with the simulation test bench, if you want to call it like this, where you communicate with this binary that is otherwise quite similar to the binary that would run on the drone. Now in your software in the loop setup here, you're communicating via various networking sockets. Yeah, so there's various TCP connections. And some of these might essentially connect to a local mission planner module. Some might connect to a local MAF proxy. And then there is a physics simulation engine. So this communication, of course, doesn't exist on the drone because this drone, the real drone, doesn't need a physics simulation. But in your setup, you somehow need to provide information to the drone. You need to get the information from the drone, what its control decisions were, its commands to the actuators. Then you kind of have this physics simulation that is now updating the environment based on these control decisions, and then sending new sensor readings back to the drone controller software. And this is, of course, now just part of the simulation setup. And yeah, that's it essentially. So roughly the setup we'll see later with other cyber physical systems as well. If we want to do some software in the loop simulation or just some simulation overall, we'll always need to have something like this. We'll need to somehow emulate the control traffic and so on. And we also need to potentially have some way for the software to interact with the physics simulation engine. So here now, for example, if you are already familiar with things like Wireshark or just network traffic monitoring or interception, you could also intercept or you should be able to intercept this TCP traffic here to kind of already see how your controlling software is interfacing with the binary. Okay, so that was already the last slides of the last lecture, so we didn't miss much. And let me just, if there's no more questions on this part, I'll just jump into today's lecture. Yes? Any command to stop the simulation? Like to pause or something like this? That's a good question. I don't know. Potentially, yes. If you, maybe you can ask it on yes?
Because for the binary file, because you need to be able to reproduce simulation sessions. I don't think I can stop it.
I mean, if then you would have to stop both the physics simulation and the autopilot software, I guess. Yeah. So you would have to pause both, because otherwise, if you would just, you mean to pause just the physics simulation part or both?
For example,
Yes. Look, I don't know, but I also have to admit I myself, didn't, play that much with the software. So if you could maybe still raise this on our AskBot, and then I can ping someone to check this out for you, okay? Okay, any other questions? Okay, very good. Then let me just quickly switch to the new slide set, where we will also talk about GPS, where some of you at least asked about before already. Okay, so last time, or partially today, just a recap again, what we talked about in the last lecture was I started to introduce kind of the common components of drones, and I also had this list of the main sensors that you might see on drones. And these included, of course, things like GPS, and then we had the IMU with the 6-axis values, yeah, so X, Y, the acceleration around the different axes that we have, and GPS would give us our location in 3D space and so on. And now, of course, if we are starting to talk about, well, security topics, manipulations of drones, then the interactions with these sensors will become quite important. So one major way how an attacker could try to interfere with a drone, to manipulate a drone, would be to start manipulating sensor readings that are recorded or processed by the drone. And I'll start here to talk about GPS, but then later we're going to mention the optical flow sensors a little bit. They will come up here. We'll talk a little bit about IMU manipulation as well. And these are all just examples for how these manipulations could go. So let me start with GPS, where we already started to talk a little bit about this as well. At least I showed you this map of the GPS jamming in the first lecture. And then there were some questions from your end as well. So I hope this is not too much of an overlap now. So what is GPS in general? Just a little bit of broader introduction here. So because it's actually a very cool system and not everyone is really knows too much about this. So first of all, my pet peeve is that the thing that is sitting in your car is not GPS. Many people call this a GPS. It's a GPS receiver. And GPS itself is this global positioning system. So in particular, GPS are the satellites that are flying in space. Yeah, at the time I wrote the slides, there was 31 satellites in operations, and they are essentially covering most of the Earth to allow then anyone to do localization based on their signals. It is maybe obvious, maybe it's not obvious, but the GPS satellites themselves, they do of course communicate with ground stations, but they're just broadcasting signals that are then received by the GPS receivers that you might have. So your GPS receiver in your phone or in your car is not directly communicating back to the satellites or something. Your GPS receiver in your phone or your car is also not talking to any other GPS infrastructure. It's just one-way communication, broadcasting signals that are sent out from the satellites to your receivers. GPS has been around for a quite long time already. The project was started in the 70s, and since the 80s, there's civilian use. So of course, GPS itself comes out of US military originally. And there is this military mode or military part of the GPS system or of GPS, and there's a civilian part. I believe I mentioned this before as well. And they use roughly the same fundamental approach. They just use then different wireless channels, for example, different encodings. In particular, the military GPS is only usable by parties that have certain secret keys that allow them to decode the signals that are being sent to them. And to this setup also, the military GPS is more secure against jamming, for example. Likely also more precise than the civilian GPS. So fundamentally, GPS allows the receiver to compute 3D location and precise time synchronization, where I mentioned this before as well. Originally, until the 2000s, the civilian GPS had intentionally degraded performance, where the precision was only around 10 meters. And then afterwards, this selective availability was discontinued because just it became so clear that there was very wide demand for precise public GPS usage as well. So since then, roughly the GPS location precision that you could get is around 3 meters. So there are some receivers that can do additional things to, in the end, get you a result that looks like it's more than 3 meters precision. But roughly, you can kind of estimate just that you would get around 3 meters precision with your location that you're getting from GPS. So I said it's not only a location, it's also a time synchronization. And the time synchronization is actually quite good from satellites in the order of 100 of nanoseconds. So this is actually potentially quite better than what many people might need for their home PCs or phones or something like this. But it is available well, I'll come to a little bit later why it's actually this precise. Very simply, the intuition could be a little bit as well. It's actually related a little bit to the speed of light and so on. The radio signals have speed of light, roughly 3 meters, precision and kinds of temporal. So because, okay, I'll get to how GPS works in a second, but GPS works on time of arrival of radio signals. And if we want to have 3 meters precision with the time of arrival or the distance measurement to satellites, then we implicitly also have a time synchronization precision of 100 nanoseconds. Yeah, I'll get to that in a second. So it's based on time of arrival signals. I said this already. Typically, you get signals from 4 or more satellites. Why do we need 4 or more satellites? Because we're solving essentially an equation system with 4 unknown, our location plus time. And to solve an equation system with 4 unknowns, we need to have 4 things for equations that allow us to then solve this equation system. So we need to have at least 4 satellites that give us some estimates of pseudo-ranges or that give us measurements of the time of arrival of the satellite signals. Given this input from these 4 satellites, essentially the receiver can theoretically just locally solve for its own location. There is in GPS, there's a so-called cold boot or a cold start or a kind of continued use. So once the GPS receiver knows roughly where it is, it becomes easier to solve these system of equations. So then you can more quickly get an update of where your location is if you know where you were maybe a minute ago or something like this. If you don't know at all where you are, solving the system of equation can take a longer time. This is why when you switch on, this is one of the reasons why when you switch on maybe your GPS receiver in a car and the car hasn't, been used in the last day or something like this, it might take a longer time for the car to get a GPS location fixed. Yes?
Or some object, can you get more precise position measurements than 3-meter estimates, or?
Yes. So let me just repeat it again. I realized we also have this amazing cube here, which I could throw around if we have questions from the audience, and then people in the Zoom call and in the recording could also hear this question. Maybe we should do that in the future. But so I just to repeat the question here. So the question was, if we have more satellites, will we be able to have a more precise location estimation? In general, yes. But so there's another constraint now. So if we have, I don't have a great visualization for this, but the number of satellites in space are somewhat fixed. And you actually have to be able to see this many satellites from your receiver. And I don't have a great, maybe you have some GPS app, for example, on your phone that can tell you how many satellites are in kind of physical view at your current location. And there might only be between 4 and 6 or 7 satellites. Given that there's 30 around the world, I don't think you will see many more than 7 or 8 satellites at any point in time. No? If you see, so the receiver should use all the satellites that are visible in a sense. Yeah, of course, not direct line of sight, but in general are, not blocked by the Earth essentially. But it might be much less than 31 satellites. Yeah. Yes?
The other alternative, for example, the Galileo, is it can it be used by others as well?
As far as I'm aware, yes. It's just that, so, Galileo for sure is, you just need receivers for this, yeah?
The main question. So for the GPS, we are seeing probably 7 of them, but in case we are using some other satellites as well from the other alternatives, then there is a chance that we are getting more precise.
Yeah. So, okay, let me just also repeat the question. So the question was that can we also, if we want to improve our precision, could we also fall back to satellites from Galileo and so on? And the short answer is, these are different systems in the sense that you need a receiver then that will support these other satellite systems as well, because there's different communication channels and message formats and so on. Yeah? So you need a multi-satellite system, GNSS or something like this. I don't really know what is being sold out there. I definitely seen receivers with support for 2 GNSS at the same time. There might even be some that support even more than this. I don't see what would prevent the receiver then from also kind of averaging the results out of these or something. Yeah, but I didn't personally do experiments on the precision of this. Yeah. For GPS itself, we actually did experiments on the precision. So I can more confidently tell you about the precision of GPS, okay? Yeah, fundamentally, the other systems are also more or less working on the same principles because it's all time of arrival measurements of signals sent from the satellites. And there's no magic that is happening. Why do we have all these different systems? Because ultimately, this critical infrastructure, if Germany would start a war with the US tomorrow, the US could somehow try to mess up GPS in Germany, and then, it would be bad if we wouldn't have our own fallback system. Yeah. Okay. Anyways, this is just a brief introduction. So how does it work? So what is the solving of the system of equation and so on? So what we have is the following. In GPS, the receiver wants to find its own location. That is, I called V here. And what the receiver does know is that the receiver knows what the receiver doesn't know its own location. The receiver might also not know its own time, but what the receiver knows through the signals coming from the satellites is at which point in space roughly the satellite currently is located. And the receiver knows for each satellite at which point in time did it receive certain beacon signals from the satellites. And from this, essentially, the receiver can compute so-called pseudo distances. So based on time of arrival and the known source, the receiver can just compute how long did it take for the signal to arrive at my current location, because it knows it was, let's say it was sent at 1 o'clock and it arrived at my location at 2 o'clock, in a very exaggerated way. Yeah. So it took 1 hour to propagate, and this means I can correlate this with the known propagation speed of wireless signals of roughly the speed of light. I can then compute how long the signal traveled in terms of distance. So I can get these pseudo distances to each of my at least 4 satellites. And then I can either, if you like equations, you build a system of equations like this, where essentially for each satellite, you build an equation where you have the location estimate of yourself, you have the known location of the satellites, and you want to minimize this essentially. You want to find in the end the V that minimizes the error here, the error which is delta, for the 4 equations at once. Yeah? Ri are the pseudo distances, and the delta is now the error that you have with respect to the received signals. So if the measurements would always be 100% precise, if you would exactly know what the location of the satellite in space is, and if your distance measurement would be 100% precise, this delta would be 0. So in that case, you should be able with 4 satellites to solve this without any error. So you should find a V that directly minus L is equal to all these distances to the satellites. In practice, you have some variability in the received time of arrival and so on. So there is some little error term that you just try to minimize when you solve for your equation here. This is very roughly what's happening. Here, the V also contains the timing, essentially. Oh, no, so delta is here used as a local time offset. Okay, but yeah. So you try to minimize this time offset here, or this error when finding your location. And you can do this with at least 4 signals. What is happening? Is that clear roughly, or? Let me maybe say differently how you could also view this. You know the 4 locations of the satellites. You have these pseudo distances. It's clear how you get the pseudo distances, no? Hopefully. Yeah. You get this from the time you know when it was sent and when it arrived at your location, and then you get this pseudo distance. With this pseudo distance, you could also essentially geometrically draw a circle around the satellite with the radius of the pseudo distance. You draw a similar circle around the second satellite, a similar circle around the third satellite, a similar circle around the fourth satellite. And these 4 circles should then ideally only intersect on one point, which is your location. There should only be one location on Earth where you would have these exact 4 pseudo distances to these 4 satellites with these known locations. Does that make sense? Yeah. Yes, but this is why, I mean, time is just another variable like your location as well. So so you will now have to solve as well for your own local time when you're solving these So here, the time difference is expressed as some kind of delta. You will need to check. So the time, of course, also influences the positions of the satellites, yeah, because they're moving quite fast. And there will be, in the end, you will need to find at which point in time, let's say you have a rough estimate of what your local time is. You could then check for a bunch of different potential time slots, at which time would I have the best fitting overlap of these four circles, if you just want to see it like this. Yeah. The four circles will only exactly overlap with the, let's say we don't have measurement inaccuracies in your pseudo distance. These four circles will only exactly overlap at one point in time. I will not go too deep into trying to prove this somehow. How we calculated it.
Really precise time.
How we calculated the delta. So okay, so realistically, so I would have to now compute a little bit in my head how long it really takes for the signal to arrive, but it's certainly less than a second or something like this. It's probably a millisecond or something like this, how long it takes for the signal to actually arrive from the satellite. So you always know within a millisecond or something like this for sure what the local time is. Yeah, just because whatever signal you're getting from the satellite, you know was sent at whatever 00 milliseconds, and you arrive at 1 millisecond or something like this, then you already know roughly what your local time is, no? You can just take the time. You could just imagine that this message contains the local time, and then you receive it. And at the point when you receive it, if we just think about simplified, if we would immediately be able to process it, then we would see, okay, now it must be roughly 00 milliseconds with plus minus something. Yeah. And then, yeah, sorry.
But then basically just collects data in certain frequencies and then evaluates them.
Yeah, so you continuously evaluate the system of equations. After you found your initial location, then you always have estimates for these things, and the optimization here becomes much easier because you just optimize around these points. Yeah. You might also do some more tracking over time and so on. We'll get a little bit more to that. We already, I mentioned Kalman filters and so on. They are somewhat involved in this in the end. But at the very beginning, if we don't know anything, we get a very rough timing just by looking at the timing, that the timestamps that are in the signals essentially. With this, we have a rough location information about the satellite positions because we can roughly compute at this millisecond where they should have been or something like this in space. And then this allows us to get a rough first estimate of the pseudo ranges, and then we can start to just minimizing errors essentially, and just over time then also make this more precise. Yeah, so this math here is certainly not part of the class. And then actually I also, at least, so this figure and so on is coming from research that we did 15 years ago or something like this. Back then, I didn't find any public libraries or whatever that will do these calculations for us. So we could also only implement it the way that we understood how it would be done. I think nowadays, I might mention this later as well, there are open source solutions to actually okay, that's a little bit of a detour again. So there are software-defined radios, which are radio transceivers or receivers and transmitters that you can relatively easily reconfigure. And you can also use them to receive GPS signals. And there are open source tools now that would allow you to actually also locally just process real GPS signals on your laptop with such an SDR. And there must be this code in those open source projects now to do these calculations. So if you're really super interested in how this works in practice, I would recommend you to just look at these open source projects that allow you to pass and process GPS signals. I don't fully remember if I have mentioned them here on the slides later, but there are these projects out there. Yeah. We had in previous years, when the class was still more focused on wireless signals, we even had exercises where we asked you to generate GPS signals yourselves and then also process them against yourself. So I know that these tools are around. Yeah, but this really goes into signal processing, wireless communication. Okay, so what is happening now? The interesting part about GPS manipulation. So now, when I talked about attacks on GPS before, we talked about GPS jamming. Yeah, and in GPS jamming, you would just add additional noise, and if you add additional noise, then simplified, it becomes impossible to see the signal, and then you don't have your 4 satellites around, and you can't find your location anymore. The alternative to just stupid jamming would be that the attacker is actually adding their own signals that either just try to confuse your receiver quite a bit, yeah, by just sending a very strong signal for satellite 1 that is a completely different pseudo range, and then your receiver might be confused about its own location or something like this. Or then in the more interesting attacks that we actually looked at in our research a while ago, and we wanted to see how possible is it to manipulate GPS in a sense of taking control over what the location fix of the victim would be. So in this setting, somehow we want to achieve an attack where the attacker is able to add or remove certain distances from these pseudo ranges. And then by having these offsets, we could somehow shift the location fix that is computed by the victim. And in the end, the interesting thing about these kind of attacks is that because this location information is not really, or the pseudo distances, this is not a number that we're sending in wireless communication. This is computed based on the time of arrival. To do such manipulations, what the attacker likely has to do is just to change the time of arrival of the wireless signals, of the GPS signals, that will then essentially have an impact on the computed pseudo distances, which will then have an impact on the location fix. Yes? Yes, let me just repeat the question again. So the question is if this is something like a man in the middle that is, intercepting the signals and then manipulating somehow. Yes and no, in the sense that we're not talking about the multi-hop kind of networked, wired network communication where the attacker can just stop a message and manipulate it and send it out again or something like this. We're talking about the wireless broadcasting channel where an attacker, to be a man in the middle or a machine in the middle, the attacker would have to somehow, first of all, probably prevent the reception of the original message and then just send its own message on top of this. Yeah. So a manipulation, there's another variant of this where the attacker tries to manipulate messages while they're on the air, if you want to call it like this. Yeah. I don't really talk about this in this lecture, but we also did some research on this a while ago. Yeah? But this is not really what's usually happening here. Here we are talking about a setting where either the attacker will have to make the original legitimate signals disappear through jamming or something like this and then inject their own signals, or control the satellites, yes, or shield the victim somehow else from receiving the original signals. Actually, what you can also, what you can do in these settings here is, because many GPS receivers will just lock on the strongest signals, you don't necessarily need to jam the original signals. You just have to be relatively stronger than the original signals, and the receiver will automatically latch onto your signals. Because the receiver likes good and strong signals, it might still see the legitimate signal, but your signal is much stronger, then it will just switch over to your signal. How this is working precisely, again, we would have to dive deeper into the physical layer of wireless signals and so on. Yeah? But for now, let me just say it could also work like this. Yeah. So it does not work like the attacker is somehow catching the signal and manipulating it and sending it out again. Yeah.
Client is only processing 4 satellites. Means generating one stronger one, it will ignore one of them and use mine and 3 others.
this is a simplification here, yeah, but there are certainly, so all these signals essentially have to be processed in parallel by the receiver. These are not, so we are not talking about discrete messages that start at some point and stop at some point, and then we have a large gap. But this is a continuous stream of information that is coming from the satellites. So even for 4 satellites, we have to essentially have 4 parallel receiving pipelines in our GPS receiver that each listens on a specific channel. Each of the satellites has its own channel, like its own frequency. So even for only 4 satellites, our receiver has to follow at least 4 satellites separately in real time the whole time. Yeah? So you could build a receiver that can follow 30 satellites in parallel, but this will never be used, and it will be, 8 times more expensive than the other one or something. Yeah? So how many channels you have in realistic public receivers at the moment, I don't know. You can maybe find it out somewhere if they would actually tell you. Yeah, but I would doubt that it's more than 8 parallel channels for reception at the same time. Yeah. Yes. Okay. So for the GPS manipulation, what did we do? So now in the next slide, I'm essentially talking about our research work from a while ago. We were quite interested in manipulating GPS because when we started to look into this like 15 years ago, there was very little to no public documented research on this. And from a purely theoretical research perspective, it was obvious that GPS was insecure because just like ADS-B, for example, there's no authentication there at all. So the data signal, we didn't look into the data signal of GPS now, but there's no signatures or something like this. There's no authentication or something like this. It's just untrusted data coming from space, essentially. So we knew theoretically that GPS can't be trusted at all. We just didn't know how difficult it would be in practice or not to manipulate GPS. And that's why we did our research a while ago. And let's just say what were our assumptions on the attacker. We assumed that the victim is using a commercial GPS receiver with an omnidirectional antenna, which is the usual case for what you have in your phone or other GPS receivers that are maybe handheld. You are in the range of legitimate signals, and you actually are synchronized to legitimate satellites already, and you are maybe getting your correct position at the beginning when the attack starts. And the receiver will lock on the strongest signals. I mentioned this already. The attacker is then physically close to the victim, has, for example, a software-defined radio, which just essentially allows the attacker to send out arbitrary signals, for example, GPS signals. And then the attacker might have 1 or more antennas to send out the GPS spoofing signals. The attacker knows how to generate GPS signals. It has precise knowledge of its own location and the victim position, for example. And then the goal of the attack would be for the attacker to send out signals that, first of all, kind of are, replace the legitimate signals when being processed in the receiver, and eventually allow the attacker to falsify the location solution of the victim. Okay? So there was 2 ways how we did this in our research, or how that we considered in our research. One is the attacker this is slightly more powerful. The attacker has some way of generating its own GPS signals. When we wrote this paper 15 years ago, you had to have access to such a big box that could be quite expensive, that is usually used to test GPS receivers, for example. So this is a box essentially with its software that would allow you to just generate civilian GPS signals. Or nowadays you can build this with open source software-defined radio tools as well. The second option would be, so here the attacker would just generate their own GPS signals because it's publicly known how to construct them. You just have to have the radio equipment to do it. The second option would be slightly more stealthy or more clever, I would say. Somehow the attacker has a way to record legitimate GPS signals separately for each of the satellites in the environment, and then replay them again with a time offset applied to them. So here the attacker would not change anything on the data layer at all. The attacker would also not have to be able to actually generate their own GPS signals. They would only have to be able to record or relay legitimate signals with a certain time offset. In both cases, then the attacker could apply essentially a specific offset to each of the satellite signals and then send this to the victim, for example, via one antenna or multiple antennas. Yes, that's a question here?
Very basic question. But the communication itself, is encrypted? How do you encrypt it? Plain text?
It's not encrypted. Yeah. Public GPS is not encrypted. Why is it not encrypted? The very simple solution to this is, first of all, it's a system from the 70s. So whatever crypto they would have in the 70s would be broken by now. The second simple explanation here is that it's a broadcasting communication to a public. Encryption would not make much sense here. If you wanted to ask about authentication, well, I said already, but it's not authenticated. So it is also difficult to authenticate things in such a setting where you're broadcasting to the public. You can only do it using asymmetric crypto. And okay, let's not dive too much into that, but that would have been also in the 80s, that was not around. And even with asymmetric crypto, you could not really solve this problem very easily. Yeah? If you have a shared symmetric key or something like this, you can't just authenticate unilaterally or something like this. Then everyone that has the same key can also authenticate. Anyways, it's not encrypted and it's not authenticated. Yeah? So anyone can produce the signals. So the second attack, which is slightly interesting, is with this relay of GPS signals. I already talked about this. You could potentially just pick up the signals and replay them with a certain time delay. The nice thing about this is this attack should even be possible for a military GPS. We never tried this in practice. I think I mentioned this before. We like to travel to the US, so we didn't want to mess around too much with that kind of stuff. Theoretically, that should also be perfectly possible because even if the signals are encrypted and even if they are authenticated, the fundamental insight is here for the second attack, I don't care about your crypto authentication if just the time of arrival of the signal is the important part. You can give me a perfectly encrypted and authenticated signal. I just see the ciphertext and I just take it and replay it 1 minute later and its time of arrival will have changed. And if the victim is doing the main thing, which is the computation of its location based on the time of arrival, just the traditional crypto authentication is just doing something perpendicular. It's unrelated to the location thing. Yeah, this is one reason why I'm starting with this example again, because this is an example where you can't use traditional crypto. This is also why I had the ATM example. To some degree, it was similar in the ATM example. You can't use crypto mechanisms to prevent this wormhole attack, this relay for the ATMs. And the same in GPS as well. You can't use traditional crypto methods to authenticate time of arrival of a signal. Yeah, but okay, military GPS relay, theoretically should be possible. I've never seen people do this in practice and, live to speak about it, but I'm sure some people experimented with this. Yeah? So for the simulators, I mentioned this already back when we did research 15 years ago, it was quite expensive. Nowadays, I have a link here to this is supposed to say open source GPS signal generators are available. So these allow you to generate GPS signals. And then there is a corresponding other package that allows you to decode these GPS signals as well. And then you just need an SDR, like a HackRF or whatever, that might be 200 euros or something like this nowadays to actually, so you could also easily build something like this now for 500 euros or something like this. You really should not do it now, personally, because we are relatively close to an airport and so on. So I would recommend you to not mess around with this too much, because this will really can have very bad consequences for whoever's relying on GPS signals in the environment. Yeah. When we did the research, we also did it essentially, we did it over wire in the end. We had the simulator and you could connect a wire and then we connected this wire to the GPS receiver. There are some people that did it over the air as well, but then usually you would either be in a bunker somewhere where you're reasonably confident that your GPS signals over the air don't reach outside, or you otherwise coordinate with local authorities that you're doing stuff like this. It's not that easy to do it. Okay, there's an explicit slide on the GPS data manipulations. So far I talked about changing the time of arrival of signals. You could also start messing around with the data that is being sent around. For example, I said before that the GPS signals contain the locations of the satellites. So obviously now you could also start to mess around with the claimed location of the satellites to convince victims of other locations of the satellites, which would influence the pseudo distances. There is, for example, one paper as well from 13 years ago where they're looking into this. At least back then, this was definitely also possible to just, you could do anything with this data if you wanted to. There was very little sanity checks being done in the GPS receivers. As far as I recall from one of the things that they mentioned here is they were, for example, GPS receiver, they could send signals to GPS receivers that would then be used for location fixes where the satellites would be on the other side of the Earth or something like this, and the signals should never arrive at the receiver. There was no check for that. They were able to claim that the satellites would, for example, sit in the center of the core of the Earth or something like this. You know, they could just mess around with this, and there was no sanity check being done in the GPS receivers. If you want to see more on this, just have a look at this paper here. Yes, and I actually don't know what the current state of the art in commercial GPS receivers is. Maybe they started to making some sanity checks there, but back then there was nothing. So now, it sounds like from what I described so far with the settings, it sounds like it's trivial to do GPS spoofing, and it would be trivial to just change the pseudo distances to get the victim to any arbitrary location. What we actually found and investigated most in our research back then was that the difficult part here is actually that to some degree, the victim, it's a stateful system, and the victim very likely is synchronized with the legitimate receivers before the attack starts. So the victim has a known location. And then if we want to transport the victim to some other location, we could start a very brute force GPS spoofing, kind of hammer down the legitimate signals, send signals that are for a completely different location. And then, of course, within the GPS receiver of the victim, or if the victim is monitoring its own location, it would then immediately see that it's jumping, 1 kilometer in a second or something like this. And it could notice this and notice an attack. It might even the GPS receiver, because the GPS receiver is itself convinced that it is a certain location, it might not even pick up our attacker signals because they are so much out of phase in terms of time and location. They're coming, the receiver is not even looking in the radio spectrum for these kind of signals because they're not supposed to be there. They can't be there. They just don't fit to the current observation window. To some degree, if you have a synchronized GPS receiver, it has a very narrow window within which it expects the next signals to come in, which is essentially more or less the window that encapsulates the local noise or something like this. Yeah, if your jamming signal or your GPS spoofing signals come from completely different location, the receiver might not even synchronize to your attacker signals. So what we looked here in the paper is that we wanted to see how precisely, how can you do such a takeover, what we call the lock takeover of the victim, in a way that is stealthy, what we called it, that would not be noticed by the victim. And essentially get the victim receiver to lock onto your attacker signals. And then after the victim is locked onto your attacker signals, then you can maybe slowly start to drag away the victim from its correct location into a location under your control. So this is a type of attack that we'll see a lot more later in the term as well. Other people also call it sometimes, for example, a boiling the frog attack, where the idea is that you start with an attack that has essentially no impact on the victim, and then over time you increase the intensity of the offset that you're inducing, and slowly you're dragging away the victim from its initial state into a state that you want to have the victim be. Yes? Cool.
So, that's where I was thinking about if you're really monitoring, for example, drone, then you need to have at least some time window comparison between what it should be and what it currently is, for example, the position. And if the distance deviates too much from that position, then you send out an alert.
Yeah, we will talk more about this later. Yeah, but this is exactly a core of some of the text and the defense as well that we'll talk about later in the term. This will come up all the time when you're trying to do these kind of manipulations of, let's say, cyber physical systems in general. There's not going to be one discrete takeover step after which you can fully control the victim, because that is going to be for stateful systems too much of a jump from the previous state to the next state. Yeah. What we looked into in the paper here is what I'm showing here on the figure is that, for example, here we have some, okay, the x-axis is time, the y-axis is an error or a location error. This is essentially the difference between the location that the victim is at, or rather the difference between here before this part, we would actually, so before this part, the victim only has legitimate signals. After this part, the attacker will start to send a spoofing signal, but the spoofing signal is designed to exactly match the correct location of the victim. And afterwards, then the victim will slowly start to synchronize to the attacker signals. And what we realized, at least in our experiments, was then that while the victim is switching over to our attacker signals, there is a bunch of kind of problems in kind of synchronization, which will lead to some bigger location estimation error. So there will essentially be some kind of jumps being performed by the location estimation by the victim, which could potentially then be noticed by the victim. And this might be a way how to detect such a stealthy takeover. So in general, for stealthy takeover, what the attacker would try to do is to match the legitimate signals exactly at the victim, turn up the power a little bit, and then slowly drag away the synchronization of the victim to whatever synchronization that the attacker wants to have. Is this intuition clear? What would happen here? So if I want to, how else could I? If somehow you are, yes, sorry.
The channel which actually receive the data.
Yes and no. Okay, let me try to think about how deep I want to dive into this now. So with synchronization, what I refer to here is, so the radio frequency is going to be the same all the time. So also the attacker signals are on the same radio frequencies. I'm talking about the temporal alignment of these things, because the temporal time of arrival of the signals is what is making the impact on the distance or the location computation. We need to somehow pull away the phase alignment a little bit. Let me say it like this. So if there would be a second copy of me talking to you, and that second copy of me is an attacker, and I'm talking to you, and you're listening to me, and at some point, the second copy of me also starts to talk, and initially it talks such a way that its audio, it will say the same things that I'm saying, and will time it such that it arrives at your ear exactly at the same time. Then our two signals will overlap and you'll just hear me twice as loud. Okay? And then the attacker will start maybe talking a little bit louder than me and so on. So the signal in your ear will be even louder. And then at some point in time, the attacker will start to talk slightly slower or faster or something like this. such that now your ear, if you have a good receiver in your ear will track that there's two copies of the signal. One is a little bit earlier and a little bit later, and will start to synchronize or just listen and tune into listening to the signal which is stronger, which might be earlier or later, which is the attacker signal. And then this desynchronization will become bigger and bigger, and your ear will kind of follow the signal that is still stronger. And I will be both weaker and also kind of out of phase. My voice will arrive too late, or it's a little bit hard to explain this with human voice, yeah. But in radio signals, you can simplify it, think about it again as just sine waves that are being sent around. And then the sine waves essentially have a different time of arrival, a phase or something like this. And the receivers will always be tuned to these sine waves. They will have to essentially follow the cycle of the sine wave precisely. And what is happening here in this takeover is that the attacker will have to initially send signals that are exactly phase consistent with the real signals, and then later pull them away. And after the pulling of away here, after this time in this attack now, the victim was completely tuned to the signals of the attacker. The location that the victim estimated again was very consistent, didn't have any errors anymore. And at this point, then the attacker could pull away the location of the victim to somewhere else. And to do this now, and this, at least back then, for us, it was quite an interesting observation that there was this kind of statefulness of the system, and that you actually, as an attacker, had to very slowly drag away the victim from its previous synchronization and previous state. What we investigated a little bit more in the paper, which is linked below here, by the way, if you want to have a look at it yourself. It's called On the Requirements for Successful GPS Spoofing Attacks. We then looked into how precisely will the attacker have to match the original signals at the victim to do this takeover without confusing the receiver too much. And for this specific combination that we investigated there, then you had to both have relatively tight control over your signal power at the victim. The time synchronization had to be within 100 nanoseconds or something like this. You had to very precisely know your own location and the location of the victim as an attacker, so that you could make sure that your signals that you send out were also arriving at the right time at the victim and so on. And then the location that you would be spoofing would initially have to be within 500 meters of the victim as well, for example, of the true location of the victim and so on. So without, I mean, the exact numbers here are not that important. What is important is that if you want to actually do this very stealthy takeover of a victim that is somewhat monitoring its own location, you had to align your signals very precisely, which is quite challenging in practice. In particular, challenging if you think about things like spoofing, taking over the GPS log of a quickly moving target, like an airplane or something like this. Yeah. So back then we didn't investigate this too much more, but we already said that this, this sounds a little bit challenging. Yeah? When we published the paper, then by coincidence, probably, I mean, there was some active US military action in Iran at that point in time, or Afghanistan, I forget. Yeah, not that important, but there was some news then that, for example, some US drones were supposedly hijacked by GPS spoofing by Iran, where when we were asked by journalists, our opinion was more that it was unlikely that this was being done because, I mean, journalists, of course, thought, we now published this results and Iran immediately implemented this to hijack the US drone. I not only I don't want this, but I also don't think that this would have been the case. Yeah. So just because of all this precision, because precisely here we found that you actually have to have very tight control over your own setup to do this kind of thing. And doing this on a quickly moving drone somewhere out in the field, we find this to be quite challenging, and there might be easier ways to then bring down drones. Yeah, just simple GPS jamming, for example, might have been sufficient in such a scenario already. Yeah? But of course, we don't know what happened here. I also still don't. There is follow-up work on this, which some of this I'll mention as well later in the slide set, but I don't think I've heard about cases since then where it was really claimed that this active GPS spoofing was done to redirect drones and so on, because it's still challenging. Yeah, so actually it's the next paper. Yeah, so there was a great paper that followed up on this by people from our former research group. So I was not involved in this, but this was from CPSS'25 by Martin Schomeyer, Vincent Landers, and Anjan Ranganathan. So Anjan was actually my office mate at ETH. Martin is still with Amaswiss, which is the Swiss branch of the Swiss military, let's say it like this. And Vincent is actually he just moved to be a professor in Luxembourg. So what did they do here? They now try to do this kind of spoofing that we predicted to be hard. They try to do it for commercial end user drones in a practical setting. Yeah? So the paper is called An Experimental Study on GPS Spoofing and Takeover Attacks. And without going too much into details here, so they built a system. They have lots of cameras to, for example, monitor the target to see where its location is. They have a relatively small setup anyway, so they have good estimate of the location of the victim. They then use, I believe they had both the legitimate and the attacker GPS signals were essentially created by them indoors with a software-defined radios. And what they found here, for example, is that, yes, first of all, you could do this. They replicated our results that you can do this spoofing even with commercial drones nowadays. But there were issues, two interesting issues that I want to highlight here for this. One that I found is that these drones that they were actually attacking had these optical flow sensors, so essentially cameras that are pointed to the ground. And now after they would take over the log of the drone, the GPS log of the drone, they would try to make the drone think it would be moving at a certain speed, although it was actually stationary. And they found that the optical flow sensor by the drones actually allowed the drone to detect that it was not actually moving because it saw the same ground all the time. And then at that point, there was a mechanism in the drone apparently to then just estimate that the GPS signal is unreliable and would essentially override the GPS signal and not believe the GPS signal anymore. So what did they do to try to get rid of this kind of countermeasure? They had to either disable the camera or turn off the light in the lab. Of course, turning off the light was a little bit easier. And in those scenarios, then the drone could not use the optical flow sensor anymore, and the GPS spoofing would actually work as expected, which was quite interesting to see. And the second thing that they found then is that, yeah, after they disabled the cameras, they found it relatively difficult to control the drones. Yeah? So what do we see in this figure here? This is time in seconds. This is acceleration that they achieved. And then they had spoofed different velocities of the drones. Yeah, so if they would spoof, for example, a very low velocity, so they would drag or move the location via GPS very slowly by 10 centimeters a second, then okay, the drone would, maybe I'm moving too fast already. So what is so let's assume, so we talked about the different modes of the drone, and there were a bunch of modes. So for example, there was this hover mode or something like this, where the drone just attempts to stay at its own location at some static altitude. So if you would do such an attack where you take over the GPS log of the drone and you then slowly change the location that is received by the drone, what do you think, what is the reaction going to be of the drone? Yes?
Different needs to be for example, from the IMUs. And I could imagine if you have some kind of monitoring that says, okay, from waypoint 1 in the mission to waypoint 2, you should not have accelerometer readings that exceed a certain interval, then you could potentially monitor it.
Yes, but let's make the setting even simpler. Let's just say that the goal of the drone is just to be statically at some location at some height. So there's not even waypoints or something like this. So now if we start to mess around and drag around the location of the drone, what is going to happen? I mean, mess around and drag around the location via GPS manipulation. How's the drone going to react? I mean, first of all, yeah. Exactly. So it will essentially react in the sense of seeing, okay, I'm supposed to be at location X. I'm drifting away from location X. So let me try to compensate by essentially going in the other direction that I'm supposedly moving. And then, of course, this will result in a real physical location change. And then the physical location change will actually not be reflected in the GPS updates because the GPS updates are still spoofed by the attacker. And I didn't actually go too much so far, but if the attacker is just using one single antenna to send out the GPS spoofing signals, then the physical location of the victim doesn't actually matter with respect to the location that is in the end computed. We'll talk about this more when we talk about countermeasures, which is not today. But essentially, the drone will think it is drifting. It will start moving in one direction, and the GPS will not reflect this move, so it might move even stronger. Yeah, and it will just accelerate. And this is a little bit what is happening here. So at the low spoof velocities, there is some acceleration that is observed then by the drone into some direction, which gets bigger and bigger. But this is, very slow. But as soon as you start to spoof a velocity of 1 meters or more, you see that the drone reacts quite violently. And then somehow there's very drastic reactions by the drone in terms of accelerations into some distances here. Yeah? So here you spoofed a 2 meter per second movement, and the drone reacts by, initially it ramps up the acceleration up to 2 meters per second, but then it actually even goes way beyond this 2 meters per second because it observes that it actually doesn't really change the location as intended. And it will just increase the acceleration. And then it will eventually trigger some fail safes or, burn through the motors or something like this. Yeah. So if you now want to guide a victim drone to a specific location, you have to start, spoofing a location, which is, in the opposite direction, essentially. And then also you have to make sure that you update the spoof location in such a way that you control the drone to take the right actual physical movements. Yes, question? Yes.
What is the thickness indicate?
So, okay, so EKF is the extended Kalman filter. I believe what happened after the EKF failsafe triggered was that it essentially went into this move back to the starting location, which in this case was just, lower to the ground. And that's why the acceleration was then lower, something like this. I would have to read the paper in detail again to see what is happening here, but essentially it stopped, it went to a fail-safe mode and then, just tried to get into an as safe. It stopped following the mission, essentially. It's just wanted to get to the ground or something, yeah? So, sorry?
Probably. Then differently because maybe the movement after
We can still just, let's try this amazing. I don't know how good you are at throwing things, but if someone wants to say something, I'm happy to pass along the cube here. This is not supposed to discourage you from saying something. It's just to allow the people in the Zoom call to hear what you're saying. Is this clear now, or we still have questions on this figure?
I have one question.
Yes, please.
So I understand the approach of spoofing the position and making the drone actually think it's drifting.
Yes.
But here the graphics actually says spoof velocity, but what I'm thinking the whole time is just spoofed position. That we're
Yes, but here in terms of spoof, yes. So here actually the location that is being spoofed is slowly moving as well. It's not a static location that is being spoofed. It's a location that is moving. So this is why it's spoof velocity. It will then, the drone will think it's actually moving with a certain speed in a certain direction here. Yeah, so this is of course already a little bit more advanced scenario as well.
Okay.
Of course, then as well, these kind of things are somewhat dangerous to do as experiments because the drone will accelerate quite a bit. 3 meters per second is already quite a bit. I can't compute it into kilometers per hour now in my head, but I think that's a fair amount of speed that the drone will then start to just move around in the room and so on. So I think I mentioned it before, for these kind of experiments, then usually researchers would somehow anchor down a drone somehow with a cable to the ground or something like this to prevent itself from rushing into the next wall or something like this. Okay, you can keep the cube for now, and then we see if there's more questions later. Okay, so the EKF stuff here is already pointing towards interesting things now. So first of all, they reproduced that we can actually do these manipulations. They also reproduced that there was reactions by the drones as expected. And now the next question is how can you actually control these things, or what is this failsafe that was triggered? Are there maybe some things in the drone already that would detect or prevent such attacks from a more reliability or just control theoretic perspective? And it turns out there are these. Yeah, I saw in the chat that people said the cube works well. Very good. Yeah. So what is the EKF then? So I very briefly introduced the Kalman filter before, and I said already we're also going to see more of this later. What is happening here is that the drone has an estimate of where it's supposed to be or what the physical process state is. The sensors that are coming in are disagreeing with the predicted sensor values that the EKF is producing. And this mismatch between the predicted sensor readings and the real sensor readings leads to an estimation error in terms of the Kalman filter. This is the variance internally that is being tracked is too high. And this is then aggregated as, how's it called here again? Here in the figure, it's called test ratio or something like this. So there is some way of keeping track of the error of the estimation of the prediction, essentially. And at some point, this error value got very high in two scenarios here, the green and the blue one. And there's just a threshold is crossed here where the drone would say, okay, my Kalman filter is working so unreliably that I can't trust my sensors anymore. Somehow my internal estimation of the system is very different to what I'm observing externally. And then I will have to go into, from a guided mode, for example, into the land mode. I have to go into fail-safe mode again. And this is something that essentially is just using parameters that are, or tracking that is done in the Kalman filter anyways. So Kalman filters will always try to keep track of how precisely where they're predicting the future readings. And here, just this threshold will then already kind of lead to some kind of detection and prevention of such spoofing just by putting the drone into a fallback kind of fallback mode that then stops the operations of the drone. Yeah? So this could of course be used as a denial of service attack, but then at least the attacker cannot make the drone go to completely arbitrary other locations. So this is to some degree also confirming what we in the earlier research said, that if you do this takeover of, if you do a takeover of GPS locations, for example, you should avoid having these very big differences between previous synchronization signals and your new signals, because it will lead to large errors in the location estimation, which could then lead to such shutdowns of the targets. Okay, does that make sense? We'll actually look more into this later, because to some degree, this extended Kalman filter, tests or variance detection and so on, this is quite similar to what otherwise from the research side was also suggested to be used as detection of manipulation. Okay, there was one. This part we actually talked about already. We're starting to run out of time again today. But so we talked about this already, yeah. So if we want to have the drone going in this direction, we would have to spoof, for example, that is actually at this location, and then the drone will try to come back to its location where it's supposed to do, and in reality go in this direction. Yeah? So we talked about this already. And this is just an overview of what the system that the authors in that paper then eventually built, and that was, well, enabled them to take over control of the drones and really move it around as well. So let me see, which part are we missing? So there's one additional part now that I will not go through today, which is related to, I just tease here the title of it, IMU spoofing. So far, we just mostly talked about GPS spoofing. But there's, of course, also other sensors, for example, the 6-axis IMU that I mentioned before. There's a number of papers now that are talking about how you could potentially manipulate such IMUs to give other readings. And we'll come back to that either in the next lecture or a little bit later in the term. So for now, let me just conclude here for today. So in addition to just catching up on last lecture slides a little bit and having nice discussions with you, we looked at, in particular, at GPS. I introduced how GPS works in general, and I tried to convince you that GPS manipulation attacks are at least theoretically quite easy to do, and in practice we can also do them. We just have to make sure that the signals that we're sending out are relatively precisely aligned and have the right power to be able to take over the GPS log of our victims and to not make them aware that there's suddenly a big jump in their location, for example. And this was somewhat predicted by us a longer time ago in research, and then also more recently shown in practice as well that it's possible to do. Just that there might be other countermeasures, not really countermeasures, but there might be other measures in target systems that are built for normal reliability purposes, like, for example, the optical flow sensors or the extended Kalman filter variance monitoring that could pose additional challenges for an attacker to take over this and need to be taken into account when you do this kind of manipulation of GPS and sensors in general. And in the next lecture, we will look a little bit more into maybe the IMU manipulation, and then also look into more countermeasures, what you could now do, at least against the attacks that we discussed so far, to detect or prevent these attacks. So see you again next week.